Hi everyone! Welcome to a breakdown of the 2013 AP Calculus BC FRQ response question number 5. This one's got a little bit of everything: Euler's method, L'Hopital's rule, and solving a differential equation. If that sounds like a lot, don't worry, because I'm going to walk you through step by step, show you how to earn every single possible point, and possibly throw in an analogy to make the concept stick. So without further ado, let's jump into part A and see what this question is all about.
Okay, so for part A, we are given a differential equation and an initial condition of f of 0 equals -1, and we're asked to evaluate the limit as x approaches 0 of f of x plus 1 over sine x. So for a problem like this, what I like to start off with is that I like to evaluate the limit of the top and the bottom separately first to make sure that they don't go to 0. However, in this case, they do. So if we were to take the limit of f of x plus 1 over sine x, we would get 0 over 0, which is indeterminate form. And since we can't really draw any conclusions from that, we are going to be utilizing L'Hopital's rule to further take the limit and find the value. So to use the L'Hopital's rule, we will be taking the derivative of the top and the bottom independently of each other. So here, the derivative of f of x plus 1 is f prime of x, and the derivative of sine x is cosine x. And before we move on any further here, I do want to clarify that another way of writing this initial condition would be 0, -1, which is essentially just a coordinate point, and here x corresponds to 0 and y corresponds to -1. Anyway, so once we take the derivative, we are going to be evaluating the limit of f prime of x over cosine x, and once we plug in our values, our 0, we are going to be getting a value of 2 as our final answer. So let's talk about scoring here. This part is worth 2 points. 1 point is earned for recognizing and applying L'Hopital's rule, and the second point is for getting the correct final answer of 2. But you do have to show the indeterminate form to get credit using L'Hopital, so you do have to acknowledge that 0 over 0 is indeterminate form. Let's move on to part B now. All right, so for part B, we are asked to use Euler's method starting at x equals 0 with 2 steps of equal size to approximate f of 1/2. So there is a convenient formula to memorize for problems that involve Euler's method, and that formula is right here. It is f of x of the new coordinate point equals f of x of the old one plus h, which is the step size, which we'll talk about in a second, times f prime of x of the old coordinate point. So I will explain this formula in depth a little bit later, but first I want to talk about what step size is. So basically we're asked to approximate 1/2 starting from 0. So our starting point is 0 and our ending point is going to be 1/2. And we're asked to use 2 steps of equal size. So what I like to do is I basically like to to actually find the step size, I like to divide the ending point, which in this case would be 1/2, by the number of steps they want us to use, which in this case would be 2. So I will divide 1/2 by 2, and divide is just like multiply by the reciprocal. So 1/2 times 1/2 is going to give me 1/4, which is going to be our step size. If they asked us to use 3 steps of equal size, then I would have just divided 1/2 by 3. So it basically works for any step size they give you. Anyway, so once you get the step size, we're going to evaluate the formula. We're going to plug in values, and I'm going to talk about it as we go. So since we're asked to approximate it with 2 steps, we're first going to plug in 1/4, which is going to be the new coordinate point, equals f of 1/4 equals f of 0, which is already given. It's what we're starting with. It's the old one, plus 1/4, which we solved here, is the step size, times f prime of 0, which right here is the old coordinate point. So once you evaluate that, we get -1 for f of 0. It's given initial condition right here. F of 0, -1 plus 1/4, which was the step size, times 2. Right here, dy dx is essentially the same thing as f prime of x. So we plug in 0 for that, and we get 2. So our answer for f of 1/4 would be -1/2. And for the next step, we do need to realize that this essentially is, again, a coordinate point. Our x value is 1/4, our y value is -1/2. So we're going to move on to the next step, which is approximating 1/2 using the previous point. So here's our new point, f of 1/2 equals 1/4, which was the old one, plus 1/4, which is the step size, times f prime of 1/4, which was the old point. So again, we're going to evaluate, and right here, we are reusing the y coordinate that we got from the previous step, plus 1/2 squared, which is going to be f prime of 1/4. So you plug it in, and then 1/4 right here as the step size, and we're going to get a final answer of negative 11 over 32. Again, about the scoring. So this is a 2-point problem. 1 point is for showing Euler's method with correct steps, and another one for the correct final value. If your math is slightly off, but if your method is solid, you can still earn a point for this part. Okay, part C, last part. We are asked to find the particular solution to the differential equation with initial condition of f of 0 equals negative 1. So we basically have to do separation of variables. I went ahead and rewrote the given dy dx to make my work easier to follow. And what we want to do here is we want to separate the variable, so we want to gather all the y terms on one side and all the x terms on the other side. And as you can see right here, on the left I have everything in terms of y, dy over y squared, and on the right I have everything in terms of x, 2x plus 2 times dx. And once we have this, we can go ahead and integrate. Whenever I have a power on the denominator, I always like to write it as a negative power to make it easier to integrate. And I'm not going to integrate this, or I'm not going to show integrating it because it's relatively simple. But if you integrate it correctly, you should be getting negative 1 over y equals x squared plus 2x plus c. Plus c here and in any integration problem is very crucial, so please, please, please don't forget it. Once you have this, we want to go ahead and plug in the given initial condition of f of 0 equals negative 1. So plug in 0 for x and negative 1 for y. And once you do that, you should end up with this. Negative 1 over negative 1, which is just 1, equals 0 squared, which is just 0, plus 2 times 0, which is 0, plus c. And once solved for c, we're going to get that c is equal to 1. Then we are going to rewrite the equation by plugging in the solved value for c. So we're going to have negative 1 over y equals x squared plus 2x plus 1. The only problem we have left here is that we want the equation to equal y, not negative 1 over y. So I'm going to flip both sides and divide by negative sign to get it in this form. Y equals negative 1 over x squared plus 2x. The denominator is factorable, so you could also write it as x plus 1 quantity squared. However, College Board doesn't necessarily require you to do so, so they don't really take any points off if you just leave it like this and don't further simplify, so I decided to leave it like that. So let's talk about scoring. Part C is worth 5 total points, which in my opinion is crazy. So you get 1 point for separating variables, 1 point for integrating, 1 point just to include plus c, 1 point for using the initial condition and plugging it in and solving for the c value, and 1 point for solving for y and not leaving it in terms of negative 1 over y. Here, if you forget to add the plus c, I'm pretty sure it's going to cost you more than 1 point because you are going to end up with the wrong final answer. So, like I said, forgetting to separate the variables or dropping the constant and forgetting about the plus c is going to cost you a lot, especially because parts A and B are only worth 2 points each, so a total of 4 points there. So this question, this part, is really what's going to determine how well you're going to do on this FRQ.
Since part C was a whopping 5 points, I thought it would be beneficial if I did a quick analogy to help you further understand the topic and to help you solve any problem that involves separation of variables that you encounter easily. So join me and consider the following. Welcome to Consider the Following. All right, so I want you to imagine that you're baking a cake right now. Or don't, because I'm about to bake one right now anyway. Anyways, so here we have our dry ingredients in terms of X. Baking powder, flour, and sugar. And here we have our wet ingredients in terms of Y. Milk, an egg, some olive oil, and vanilla. So, this recipe that I have in my head, because I don't need like an actual recipe, I'm a pretty good baker, right?
No.
Okay. So this recipe I have is our differential equation here. But the problem is, we have all of these wet and dry ingredients jumbled in a big bowl together, unmixed and like uncombined. What would happen if you were to bake it? The results wouldn't be very pleasant, right? You wouldn't really want to eat that. Like everything unmixed, uncombined. It wouldn't be very nice to eat. So what are we gonna do? Well, like I said, we're gonna separate the ingredients. We're gonna first of all combine the dry ingredients and then combine the wet ingredients. And this is separation of variables. Next, you follow the steps in your recipe, integrating each side, and you mix both sides, both bowls, until smooth. Now, every good recipe has a special twist, right? And in calculus, that's your initial condition. It's the secret ingredient that makes your solution uniquely yours. So by the end of this, you just don't end up with a function, but you have your own personal function baked to perfection, right? Was that too much like Bulai?
What do you mean?
Like the let's consider the following stuff and all that?
Maybe. Yeah.
Guys, if you're ever confused on the AP test, remember, inertia is a property of matter. Thanks for joining me and consider the following. Okay, that was a full run through of the 2013 FRQ number 5. Let's quickly recap what we did. We used L'Hopital's rule to evaluate a limit. We also went over Euler's method formula, and we also solved a differential equation like it was a piece of cake. If you want more practice, I do recommend checking out the 2011 FRQ number 6, which has more Euler's method problems. And also Khan Academy has some great videos on both differential equations and Euler's method. That's it for today. Thank you so much for watching and hope you crush that AP exam. Bye!